Okay, so we're going to talk about interpreting our r squared and our slope and y-intercept today. We're going to look at a worksheet that I have in, it's about the distance from Atlanta and the cost of a plane ticket, basically. In that worksheet, 48% was the r squared, okay, and we'll look at that in a minute. We talked a little bit yesterday about the cost of a pizza. If you go to a pizza place and they say charge you $8 plus $1.50 per topping, that has an algebraic relationship with an r of 1, because it's a perfect line, and an r squared of 100%. But 100% of the variability in price is not explained by toppings. The number of toppings is changing. When the number of toppings changes, the price changes, right? And so to describe r squared, it's talking about how the variability in the x variable affects the variability in the y variable, and how much can the model account for that. So we say that the differences in the number of toppings explain 100% of the variation or the differences in the cost of the pizza, right? It's how we're changing the number of toppings that affect how the price changes. And it's 100% of the reason the price is changing, right? Because they're charging you $1.50 per topping. They're not adding other things into the price of your pizza. But that's not the case for most situations. We look at this distance from Atlanta and the variability in price, and only 40%, 48% of the variation in price is explained by how far you are, the changes in how far you're going from Atlanta. There are other things that they put into the cost of your ticket, not just how far you're traveling. That also means that the other 52% is explained by other variables. And it's due to other things that are unexplained, things that we maybe can explain, and also sampling error. Okay? Now later on in more advanced statistics, you get into multiple regression, where you can actually make a regression with several variables on the x-axis, and then you have one variable on the y-axis, but that's a little bit above our content right now. The next thing is interpreting your slope. Remember from algebra, slope is the change in y over the change in x. So when it asks you about the variables or the units of the slope, right? I think one of the questions on the homework from, Tuesday, asked you, what are the units for the slope? And it was, I think, price on a house. Number 15 said the price and size in square feet of 117 homes. The regression predicted the price, so that was the y value, in thousands of dollars. So the change in y is the thousands of dollars. That's your y units. And then your size was in square feet, per square feet. Okay? So when you look at buying a house, for example, one of the measures it has, like on Zillow and the sites, what are the other ones? Trulia, there's all kinds of sites for home buying, is one of the things it shows is the price per square foot, right? So how much are you paying per square foot for that house? So in Canyon Lake, if you are looking at a house on the water, your price per square foot is really high, because you could be looking at a house that's only 1,300 square feet, but they're asking $900,000 because it's on the water. So your price per square foot is really high. If you're inside and you're not on the water, the price per square foot goes down because you don't have that water access, and you actually get a bigger house for more money. Like those are the measures that people use a lot of times when they're comparing homes. But the units can be described as, the slope can be described as the changing in the x and y units, right? If our slope, we don't have a slope for this equation yet. It's actually 0.061. Okay, that's from number 21. The slope of 0.061 means that the price increases by 0.061 thousands of dollars, or could I say $61 per square foot. If I multiply that by 1,000, we could say the price varies, the price increases $61 for every one increase in square foot for the size of the house. So another measure is we have this weird equation that says that we can use the cricket chirps to estimate temperature. If we count the number of chirps per minute and then divide by 4 and add 40, that will give you the temperature of the cricket's location. So how would we collect such a relationship or discover such a relationship? We collect the data on temperature and the number of chirps, and then we make a scatter plot. If there's evidence of a strong association, then the next question is about the line. Someone claims the crickets, for crickets, it's the degrees in Fahrenheit is 40 plus 0.25 chirps. Interpret this slope. This slope means the temperature increases by 0.25 degrees for every one increase in number of cricket chirps. So your slope is the y increases this much for every 1 unit increase in the x. And we're going to have what we call cookie cutter statements that we're going to use to state these things over and over again in the same manner. So let's look at our distance and fair worksheet. This homework assignment, this is actually whatever we don't finish is your homework. Okay, so we're going to do this kind of together. So we're looking at a scatter plot for the distance from Atlanta and the airfare. Okay. Find r squared is the first thing we're asked for. We have the data, and it gives us our summary statistics, the mean and the standard deviation for the distance, which is our x, and the fare, which is our y. So we have our summary statistics and the correlation. If I'm given correlation, how do I find r squared? I square that number. 0.694 squared is 0.48 something, right? Yeah, I just gave that away on the last slide. 0.482. So my r squared is generally reported in a percentage. Okay. So 48.2%. Now here's where our cookie cutter statements come in. Explain what r squared means in this context. It means the variation in my x variable, okay, and that's distance from Atlanta, okay, so I'm going to create these spaces, right, that every time you write this, you're going to just change that blank based on what the problem is about. So the variation in distance from Atlanta explains 48.2%, that's your r squared, of the variation in the y variable, fare. You can swap the word variation with differences. And you can also swap the way you say it. You could say the variation in fair is explained by 48% of the differences in distance from Atlanta. So if you switch it around, then the y variable is explained by 48% of the changes in the x variable. But those words variation are super important. If you leave them off, the interpretation is wrong. Okay? So these become really important for us to really just memorize how to say them and be consistent. Every time you're going to say it the same way, you're going to write it the same way, so that you make sure you're saying it correctly and interpreting it correctly. So the next thing it asks for is to find the slope of the regression line. Do we remember our equation for the slope? That's the equation of the regression line. Y hat equals b naught plus b1x. Yep, there's an r in there. Y over sx.
What does that say instead of r?
What? You said b naught. Okay. So the slope is the correlation times the standard deviation in y over the standard deviation of x. Okay. Change in y over change in x has always been slope, right? Rise over run. Rise is the y value, run is the x value. So that's how you remember which one goes on top. Y has always been on top for slope. Okay, so take a second and calculate. Here's a hint. This is your sx, and this is your sy. Right? Standard deviation for the fair is your sy, and the standard deviation on your distance from Atlanta is your sx, and r is your correlation. Okay, so we have 0.694 times 0.563, oops, that's not right. 56.37 divided by 497.8, and that's 0.0786, rounding to 3 decimal places. How did I then find the y-intercept? Plug in what we know, right? We know the slope of y. The equation is b naught, which is your y-intercept, plus b1 times x. But we are going to plug in the mean for x and the mean for y because that's the one point the line goes through, and solve for b naught. So what's our mean for y? So we have 244.33 plus b naught, or equals b naught, plus b1 0.0786 times the mean of x, 853.7, right? And you can solve for b naught. Okay, you will be asked to do some of these in the homework soon, and very likely that there will be a multiple choice, possibly a free response that asks you to find the equation of the regression line from the summary statistics. So I got 244.33 equals b naught plus 167.101, and then I got b naught equals 177.23. Yeah? Subtract the 67. And remember, you're not rounding in your calculator as much as possible. So write the linear model. Okay? This gets students every time. The model is the equation. It's not the graph. Okay? The model is the equation. So its y value is fair. So fair hat equals 177.23 plus 0.0786 distance. We're going to use the variables in our equations, not x and y, the words, so that when someone looks at your equation, they don't have to look anywhere else to figure out what variable is x and what variable is y. Okay? So can you estimate the fare for a 200-mile flight and a 2,000-mile flight? Plug it in. So take a second and do that. Okay, so we're really just plugging it in. Fare hat. Remember, the reason why we put the little hat on there is because we're just predicting, based on our model, what we think a 200-mile flight would cost. That's approximately $192.95. Remember that whenever you are dealing with money, you are always going to round to the hundredths place because of cents, right? And then when you plug in 2,000, you should have got 334.43. Yeah? So can you compare what the model predicts to what actual prices were? Jacob. That's okay. Yeah, especially if you weren't rounding. Like if you kept your equation with all the decimal places, you're going to be off by a couple dollars, and that's okay. And that's understood on both my exam and the AP exam. Like if I get a problem and it's off like that, sometimes I'll just do the calculation in my calculator without rounding to kind of figure out what you did. If it's off enough to where I'm questioning it. Okay, so but I will always check. Okay, so it's okay to be off by a little bit. Now, the difference between what the model predicts and the actual price is called what? The residual. Okay, the residual is the difference between the actual price and what the model predicts. It's the actual minus predicted or observed minus predicted. So those differences can be seen if we look at 200, we're at about 192. And we look at 2,000. We don't have one exactly 2,000. It was 334. Okay, so what I just did was plot my 2 points. Okay, that's what 8 says. Using those estimates, draw the line on the scatter plot. You are not going to ever draw your line on the scatter plot by looking for 2 points and just connecting them there. You need to actually find 2 predicted values. So if you're not given 2 values to predict and your graph looks like this, you take the lowest number, 200, and then the highest number, 1,800. You plug them into the equation and then you draw your line. We don't look at it and be like, oh, this looks about right, if you're actually asked to draw a good line. So my points are here. This is 8. So we plotted the point, 200, 192.95, and then we plotted the point 2,000, 334.43. Of course, it's not exact, right? But it's close enough to give us a good regression line. Okay? And we can't use slope-intercept form either, because there's a gap in our graph, right? This graph doesn't continue the x-axis all the way to where we have the origin, right? There's this gap here that's not connected because this would need to be much higher in order for it to go from 0 to 150. So we can't use slope-intercept form to draw the graph either. Okay, so that's where we pick 2 points, plug them in. Now, what does the y-intercept mean? When we talked about the pizza, the y-intercept was the cost of the cheese pizza with no toppings, right? It was your base cost. What would your y-intercept mean in this context? Distance from Atlanta and airfare. So again, your y-intercept is when the x is equal to 0. Sometimes it makes sense in the context of the problem. Sometimes it does not. If you're talking about height and weight of males, you're not going to say that when the height is 0, they weigh this much. If you have no height, you don't exist, you have no weight, right? So it has no meaning in context. You can still interpret it and say, well, if height were 0, then the weight is expected to be this. And we use this cookie cutter statement that you see over here. We have 2. Our model predicts, okay? I changed the wordings from based on this model because the AP scoring guides specifically asked for wording that says that you understand that this is just a prediction. So we change it to our model predicts, and now it understands that we are predicting something. We know it's not going to be exactly that. So our model predicts if the distance from Atlanta is 0, we expect the fare to be approximately $177.23. And then we could say this would be a base fare for tickets. Okay, if it's really outrageous, like it's negative, and you're talking about height and weight, you say, well, this doesn't have much meaning in this context, but you still interpret it. So we're going to write here, our model predicts if the distance from Atlanta is 0, we need words like we expect, approximately, because we know it's not going to be exact. It's just based on the data we are using here. Airfare changes frequently, so if we did the same study a month from now, all of the prices could be different. Okay, so just based on the model that we made, this is what our model predicts. The fare, Hold on, I forgot the whole thing I just spent time talking about. We expect the fare to be approximately $177.23. In statistics, everything is our model predicts. This is what we expect. It should be approximately. We are never certain. We are never 100% certain that anything is going to happen, because it changes every time we do a new study, because there's always some natural variation. Okay. And so for our cookie cutter, this is your X variable. This is your Y, and this is your B naught. Okay, there I have a file in the modules that says cookie cutter statements. Hold on. So we're going to find the predicted by plugging this in. Yes.
I was gonna mention how Las Vegas has the same distance, you have to do the same amount as well. From Atlanta to Las Vegas, it's 17.19, but since it's staying in Los Angeles,
But it's not the same price?
you got a point.
No, I'm just noting that That's why there's so much variation. Is it more or less? They're like, oh, you want to go to Vegas? Okay, we're going to charge you more. Right? Like to us, flying to Vegas is, or going to Vegas is not, it's like this short little flight if you're flying. It's a pretty decent drive if you're driving. But because we are so close, Vegas is just like, oh yeah, Vegas is nearby. We go to softball tournaments in Vegas. You know, we go to volleyball tournaments and cheer competitions in Vegas. But for people on the East Coast, Vegas is a big flight, right? It's like a 3-4 hour flight depending on how many connections. So they sometimes can charge more. So if our fare is predicted to be $312.34, remember the residual is the actual minus predicted. So that's 212 minus 312.34, which is negative 112.34, or no, 100.34. I can subtract, I promise. Okay, a negative residual means the cost is less than we would expect. The cost is less than our model predicts. A positive residual means the cost is more than our model predicts. Okay? Positive residual means that the fare is more than the model predicts. And the negative residual means the fare is less than the model predicts. And negative residual isn't always bad. I mean, that's a good thing, right? It's good to pay less than what you were expected to pay for something, right? It's bad to pay more than what you're expected to pay for something. So it depends on the situation whether a negative residual is good or bad. Okay, so I don't expect you to do the back of this worksheet